Hi everyone. So here is a semester 1 graphing review for all of the graphs that we have covered so far in honors precalculus. So we do have a really long list. There's actually 15 different functions or types of functions that we're going to talk about today. So let's get started. So the first one is a linear function, which should be pretty basic by now. The parent function is just f of x equals x, and of course that's just a linear function that looks like this. It comes from, another form of linear functions is y equals mx plus b, point slope, or the slope-intercept form, of course, where m is the slope and b is your y-intercept. All right, absolute value functions. So absolute value functions look like this. For the parent function, the vertex is going to be at the origin. However, depending on your transformations, your vertex will be at HK. So remember, this is a horizontal translation and this is a vertical translation. And of course, this A value is really going to determine the slope of your line. So the slope of this side is actually A, and the slope of this side is just the opposite of that. So that is always going to be the case. For a quadratic function, this is also one that we've done a ton this year, so it should be very familiar. Of course, it is a parabola with a vertex at the origin for the parent function. However, depending on the transformations, your vertex might shift along with other things. So you should be very comfortable in working with both the standard form or the vertex form of quadratic functions. Now there's different ways to find the vertex. If you are in standard form, we find the x value of a vertex using negative b over 2a, and then you substitute that in to find the y value. If it's in vertex form, our vertex is simply hk. So make sure you're comfortable working with both versions. Now, most likely, if I asked you to graph a linear absolute value or quadratic function, it would be in the form of a piecewise function, because alone they're a little bit too easy, I think. So here's an example of a piecewise function. We're just going to do a quick review on how to do that. What I want to remind you guys is that you need to be careful about when you're using open or closed points. So in this example, we have a graph who is represented by a linear function, everything 1 and to the left, and is represented by an absolute value function, everything to the right of 1. So when we're actually at x equals 1, there should be a closed point for the linear function and an open point for the absolute value function. So let's start by graphing 2x plus 3. I'm going to give myself a few points. So remember, 2x plus 3 is just a linear function whose y-intercept is 3 and whose slope is 2. So it looks like this. Notice I've stopped at x equals 1 because to the right of 1, I actually am going to use this other function. But also please notice that this point is closed because this is where 1 is defined. Now for the absolute value function, this is an absolute value graph with a vertex at 2, 0, because my h value is 2 and my k value is 0. The slope is 1, so it kind of goes up to the right like this, and it will go over to the left like this, and it will have an open circle at 1. So it still needs to go all the way up until x equals 1, but notice that if you don't have that or equal to sign, it's going to be open. Okay, so radical functions. Radical functions, it's really easy to just make a t-chart for some of them, but if you know the general shape, you can just shift them according to your transformation rules. So let's start by graphing the square root of x. That's our parent function. So of course the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. Notice I'm picking perfect squares. So our graph is going to look something like this. One thing I do want to point out is that you can't take the square root of a negative number. So there is a domain restriction here. Another thing I want to point out is that if you're taking the square root of a positive number, it will never be negative. So there's also a range restriction. So this is the parent function for our radical function family. I do want to point out that there is no asymptote. It's not approaching a number but not quite getting there. It's simply just stopping there. Now, of course, if there was some sort of horizontal or vertical transformation, you could end up with a graph to the left or below. So below the graph, you will also see the transformation form of any radical function. Now, this is for square root. I do want to remind you guys that if you had cube root, we would actually have a graph over here because you can take the cube root of a negative number. So a cube root function would look something like this, and continuing on to the blue. But this was just square root, so it stopped at the origin. Okay, so for a rational function, this one we did spend quite a bit of time on because it's a little bit tricky. So we'll start with the parent function. I can see by looking at my function 1 over x, there's definitely going to be a domain restriction here. It is a fraction, and we know that the denominator can never be 0. So in this function, x cannot be 0, which means we're going to have a vertical asymptote at x equals 0. Now, these types of graphs will also have horizontal asymptotes oftentimes, and the reason for that is if you start plugging in numbers, you're going to notice that your numbers are getting smaller. You have 1 over 1, 1 over 2, 1 over 3, and if you keep going to the right, you could have 1 over 1 million. It's going to be a really, really, really tiny number, but it will never quite reach 0. It's actually impossible to turn that function into 0, which is why we have a horizontal asymptote. So you're going to end up having a graph that looks something like this, and then it's reflected over the origin, and it looks like this. So this is what the parent function looks like. So either you could use your rules of transformations to graph your functions, and notice, if you have a horizontal shift, it will move your vertical asymptote. If you have a vertical shift, it will move your horizontal asymptote. Or we can use the rules that we talked about throughout the semester for finding vertical and horizontal asymptotes. So vertical asymptotes essentially will occur wherever you have a domain restriction. And you can find domain restrictions by setting your denominator equal to 0, because of course your denominator can never be 0. One thing I do want to point out is that sometimes you won't have an asymptote. You will actually have a hole in the graph, and that only occurs with something like this. So let's say we have x plus 1 over x minus 2 times x plus 1. So you might notice that while there are two domain restrictions, x cannot be 2 or negative 1. However, the x plus 1 factor actually cancels out. So that's kind of a removable discontinuity. So this will become a hole in your graph, but 2 will remain an asymptote. So just look out for that. Not every domain restriction becomes an asymptote, because if it does factor out of your function, it's simply a hole. So just something to look out for. Now, to find horizontal asymptotes, we're going to consider this part of our function. We really only care about the largest degree in our numerator and denominator and the coefficients of those values. So if we have ax to the power of n and bx to the power of m, there's 3 cases. Case 1 is if the degree in your numerator is smaller than the degree in your denominator. So if that happens, we're essentially dividing by an increasingly large number. The numerator will never really keep up, so that number is going to get really, 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 really tiny, and therefore we'll have a horizontal asymptote at y equals 0. Case 2 is if the degree in the numerator is the same as the degree in the denominator. So if this happens, they kind of cancel each other out. So all you have left is that the ratio of your coefficients, a over b. So that is what your graph will approach as x is getting really large or really small. And the third case is if the degree on the top is larger than the degree on the bottom. So if the degree on the top is larger, your graph is actually just going to approach positive or negative infinity. It's going to keep going up or down forever. So there's not going to be any horizontal asymptote, but you might have some other type of asymptote. So you could have a slant or even an oblique asymptote. So we only did problems in class where the degree on top is exactly 1 degree larger than on the bottom, and that's when you use long division of polynomials to find the equation for that slant asymptote. So while there's no horizontal asymptote, I would still expect you to be able to find and graph the slant asymptote, which for our purposes will be a linear asymptote. So those are the 3 cases you need to watch out for. And if you know to look out for these things, it shouldn't be too bad. But you just need to remember that all rational functions have at least 1 vertical asymptote. They might have more, and they most of the time have a horizontal asymptote, or if not, they will most likely have a slant asymptote. Okay, polynomial functions. There's what I like to call a 3-step process to graph these. If I give you a polynomial function on the final exam, I will give it to you in factored form because I'm testing your ability to graph, not to find the zeros. So there's 3 things you need to do. The first thing you need to do is look at the lead coefficient, which will tell you the end behavior of your graph as x approaches positive infinity. So if your lead coefficient is positive, your graph will go up when you're moving to the right. And if your lead coefficient is negative, your graph will go down. So once you know what's happening on the right side of your graph, you can look at the degree of your function to determine what's happening on the other side. So if your function has an even degree, it's going to have the same end behavior, and if it has an odd degree, it will have opposite end behavior. And then from there, all you need to do is plot the zeros and then kind of fill in the puzzle. So you have to make sure that your graph only crosses at the actual x-intercepts given from your equation, and you have to make sure that it matches the end behavior that you determined from steps 1 and 2. So in order to do that, you do need to know what happens when you have multiple roots. So like what happens when you have a double root or a triple root or any odd or even multiplicity. That's what they're called. So we're going to address all of those things in this one example. So remember, step 1, look at the lead coefficient, which in this case is negative. So I know that going to the right, my graph is going to go down. Now I'm going to find the degree, so I pretty much count up the zeros. I have 2 here, 1 here, and 3 here. So my degree is 6, which is an odd number, which means my end behavior will be the same. Since it's going down to the right, it will be going down as we move to the left. Now let's plot our zeros. So here we are going to have a 0 at 0, and it's going to be a double root. We're going to have a 0 at x equals 3, and we're going to have a 0 at x equals -2, and that's actually going to be a triple root. So let's plot those points. So here's 0, here's 3, and here's -2. So let's start with that triple root at -2. Whenever you have an odd multiplicity, you're going to approach the 0, you kind of slow down, and then you keep going through it. So it kind of makes that semi-S-shaped shape, I guess. So this is true for any odd multiplicity. Okay, so now let's address that double root that's happening at x equals 0. So when you have a double root or any even multiplicity, it actually touches the 0 and then turns back around. So it actually doesn't cross through completely. So once again, this is true for any even multiplicity. And then if you just have a regular single root, like at x equals 3, it's just going to go straight through. No slowing down, it doesn't touch and turn around, just straight through. So there is the simple 3-step process to graphing any polynomial function. All right, exponential functions, the parent function for to the power of x is going to have a similar shape to any other parent function. So there was technically going to be a different one for 3 to the x, 4 to the x, e to the x, any of them, but they have the same general shape and characteristics. So we know that any exponential function is going to go through the point 0, 1, because any number to the power of 0 is 1. And of course, if you plotted some points making a t-chart, we know, okay, 2 to the power of 1 is 2, 2 squared is 4, so we know that it's going to get bigger going this way. Now, I do want to remind you what happens with a negative exponent. So a negative exponent does not make your answer negative. Remember, it flips that value, so it actually equals 1/2. 2 to the negative 2 makes 1 over 2 squared, which is 4. So you might be noticing that the values are getting smaller and smaller. But if you think about it, there's no possible way to raise 2 to a power and have it equal 0. So there's actually going to be a horizontal asymptote at y equals 0. So that's what the parent function looks like, and you can shift it according to our rules of transformations, or of course you can always try making a t-chart. Now the next graph we're going to talk about is a logarithmic function, and we know that logarithmic functions are inverses of exponential functions. So you guys are going to see that essentially all of the x and y values are simply swapped, and it also is going to look like a reflection over the line y equals x. So it's kind of interesting. So you're going to see a graph that looks like this, and you're also going to see that instead of a horizontal asymptote, we're going to have a vertical asymptote. So let's have a look. So any logarithmic function is going to go through the point 1, 0, because if you have the log of 1, any log with any base of 1 will always equal 0, because any base to the power of 0 equals 1. That's how logarithms work. So you're going to have something that looks generally like this. This is going to be the general shape, and it's going to have a vertical asymptote now at x equals 0. So I always recommend, if I'm graphing a logarithmic equation, actually rewriting it as an exponential equation, creating a t-chart, and then swapping the x and y values. I think that's usually the easiest way, because it can often be difficult to make a t-chart for a logarithmic equation unless you're using a calculator. Okay, now we're going to cover our 6 trigonometric functions. So for the sine parent function, we know that has a period of 2 pi and an amplitude of 1. So remember, I like to split up all of my trig functions into 4 parts, and it's going to go up to positive 1 and down to negative 1. Now on my x-axis, I'm not actually counting by 1, I'm actually counting by pi over 2. I split up 2 pi into 4 parts. So if you are not counting by ones, you need to label your units on your graph. So sine always starts at the midline, so it's sine of 0, 0, and then it goes up to the maximum, midline, minimum, maximum. So this is one full period of sine. And we can go another period to the left if we want. So minimum, midline, maximum, midline. So there you have it. So below you will see the rules for the transformations here. Really the two things that I want you to know is how to find the period and how to find the amplitude. So remember, amplitude, once again, is just the distance from the midline to the max or the midline to the minimum. So since it's distance, that's why it's absolute value. So that's easy to find. It's just the absolute value of our A value. Now to find the period, it's just 2 pi divided by B. So if you notice where B is really just a horizontal stretch or shrink. And we know that when we're working with a horizontal stretch or shrink, we actually always multiply by the reciprocal. So maybe don't think of this as dividing by b, but multiplying by the reciprocal of b. So you're taking your parent function period, which is 2 pi, and you are adjusting it for that horizontal stretch or shrink. So that's really what's happening. But either way, I'm going to find the period, and I'm always going to split it up into 4 parts. So just make sure you label your coordinates, your axes appropriately. Okay, now we're going to talk about cosine function, very, very similar. Still has a period of 2 pi, amplitude of 1 for the parent function. Really the only thing that's different is what I like to call the starting point. So the cosine of 0 is 1, so it's actually going to start up at the maximum. And it looks like this. It still hits those same 4 quadrants, just like in a unit circle. And we can even go 1 period to the left. And there you have it. So there's 2 full periods of cosine, and you find the amplitude and period in the same way as sine. All right, so now we're going to talk about tangent and cotangent. So tangent and cotangent both are going to have vertical asymptotes, so it's really important to know where those occur. So tangent I like to think of as centering around the y-axis, so I go 2 to the right, 2 to the left, and that's where I'm going to find my vertical asymptotes. So the period of pi is actually, or the period of tangent is only pi. So that means that if I'm splitting pi up into 2 parts, this asymptote is at pi over 2, and this asymptote is at negative pi over 2. And we would have repeating asymptotes occurring every pi distance apart. So now let's plot some points. And of course that would make this pi over 4. So tangent of 0 is 0. The tangent of pi over 4 is 1. So we have a coordinate at pi over 4, 1. And the tangent of negative pi over 4 will be negative 1. And then you get something that looks like this. So this is 1 full cycle, 1 full period of pi. So if you want to find the period of pi, there is a little formula. This time it's just pi over b because the parent function period is just pi instead of 2 pi like sine and cosine. For tangent, your asymptotes are centered around the y-axis. All right, so cotangent looks kind of similar. It also has vertical asymptotes, but those will occur at different locations. So cotangent actually has a vertical asymptote at 0. Then I'm going to split that up into 4 parts, and that's where its next asymptote will occur. It will occur pi units apart, so at x equals pi. So from here, we are counting by pi over 4, and we have a coordinate right here. Now, the other thing about cotangent is it looks like now it's decreasing, so it's kind of moving in the opposite direction as your tangent function. So it looks like this. There you have it. We can even add in another full period to the left if we want. And there you go. So just make sure you know where the asymptotes of tangent and cotangent are. So cotangent, you have one on the y-axis. Okay, the last 2 problems we have, or graphs we have to, or functions we have to graph, sorry, are secant and cosecant. So to graph cosecant, we'll start with, I have a 3-step process. We're always going to start by giving ourselves a guideline graph using our sine function. And that's because cosecant is the reciprocal of sine, 1 over sine. So I'm going to lightly, or in a dotted line, graph my sine function. So it goes up to 1, down to negative 1. So it looks something like this. Okay, so since cosecant is the reciprocal of sine, I know that if sine is equal to 0, cosecant is going to be undefined because you can't have 0 in your denominator. So wherever sine is 0, which is at the x-intercepts, I'm going to draw a vertical asymptote. So that's step 2 of that little 3-step process. So once again, see, this is occurring because wherever sine is 0, cosecant is undefined due to the fact that they are reciprocal functions. So I have all of these vertical asymptotes. I have one at pi, 2 pi, negative 2 pi. And then you just graph cosecant from the maximums and minimums of your guideline function. So I actually have a coordinate here. And then you end up having what looks like a bunch of little parabolas. So this is 1 full cycle. Both parts make a full period of cosecant. And we can do a second full period to the left as well. So there you have it. Essentially, if you can graph sine, you can graph cosecant. So you might guess that we're going to do that same process to graph secant, except we're going to be using cosine as our guideline function. So once again, wherever cosine is 0, secant is going to be undefined. So let's start by giving ourselves a guideline graph. I always make my 4 quadrants. I label my axis. And cosine starts at the maximum. There you go. So wherever I see an x-intercept, I'm going to draw a vertical asymptote. So I have one at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and it would continue every pi units apart. And then all I have to do is find my maximum and minimum values and draw in my little parabolas. And there you have it. Okay, so this was just a really quick review of all of the different functions that we've talked about. I really recommend going back and finding examples and actually practicing graphing all of these different functions on paper by hand. I don't think that watching this video will be enough to prepare you completely for the final exam, so make sure you spend some time and put in extra work in practicing all of these graphs. All right, thank you for watching.